Application to equally likely outcomes. Now, in our previous lessons, we spent a lot of time establishing the theoretical foundation of conditional probability, learning the formal definitions and the logic behind how one event affects another. Today, we're going to look at what happens when we apply those theories to experiments where every single elementary event is equally likely to occur. Think of things like rolling a fair die or flipping a coin. In these specific scenarios, calculating conditional probability becomes much more intuitive and less abstract. You see, in these cases, the probability of any event is simply the ratio of the number of favorable outcomes to the total number of outcomes in our sample space. The real magic happens when a condition is introduced. When we are given a piece of information, a condition, we essentially shift our focus. We stop looking at the original large sample space, which we call S, and we move our attention to a reduced sample space, which is defined by the event F that has already occurred. To keep our math precise, we will continue to use the general formula we've learned. The probability of event E given event F equals the probability of the intersection of E and F divided by the probability of F. However, because we are dealing with equally likely outcomes, we can use a much simpler version of this formula. We can express the probability of E given F as the number of outcomes in the intersection of E and F, divided by the number of outcomes in event F in this notation. N of F represents the count of outcomes in our new, reduced event F, and N of the intersection of E and F represents the count of outcomes that are common to both event E and event F. Welcome, everyone. Today, we are moving into a very practical area of our study, the application to equally likely outcomes. As we move through the next few slides, I will show you exactly how to apply this simplified counting method to real-world problems involving families, cards, and dice. Basic probability values. Now, so far, we have been looking at how to solve problems by counting individual outcomes, like when we list out sample spaces. But in some problems, you won't be given a list of outcomes or a sample space directly. Instead, you might be provided with the actual probabilities of the events themselves. In these instances, we don't need to count anything. We simply apply the general formula we established on the previous slide directly to the numbers provided. Let's look at a concrete example to see how this works. Suppose we are given that the probability of event A is 0.6, the probability of event B is 0.3, and the probability of both A and B occurring, which is the intersection of A and B, is 0.2. Our goal is to find the conditional probability of a given B. Let's walk through the step-by-step solution together. First, we identify our given values. From the problem, we see that the probability of B is 0.3, and the probability of the intersection of A and B is 0.2. Second, we apply our conditional probability formula. We know that the probability of a given B equals the probability of the intersection of A and B divided by the probability of B. Third, we substitute our known values into the formula. This gives us 0.2 divided by 0.3. Finally, we simplify the result. 0.2 over 0.3 is the same as 2/3, which is approximately 0.67. As we move into the next few slides, you'll see how this same logic applies when we go back to counting outcomes in more complex scenarios, like family compositions or drawing cards. Family composition. Now that we've seen how to apply the formula using basic probability values, let's move on to a more practical application. Problems involving family composition are classic examples of how prior information reduces the sample space. This is a perfect way to visualize the concept of a reduced space that we discussed in our first slide. Let's look at an example. A family has 2 children. Given that at least one of the children is a boy, what is the probability that both children are boys? To solve this, we'll follow a step-by-step approach. First, let's define our original sample space, which we'll call S to keep things organized. Let B represent a boy and G represent a girl. In a 2-child family, the possible outcomes are BB, BG, GB, and GG. Note that I'm listing the first letter as the elder child. So our total number of outcomes in the original sample space is 4. Second, we need to define our given event, which we'll call F. This is our condition. The problem tells us that at least one is a boy. Looking back at our original list, which outcomes satisfy this? We have BB, BG, and GB. The outcome GG is now impossible because we know there is at least one boy. Therefore, the number of outcomes in event F, which we write as N of F, is 3. This is our new reduced sample space. Third, let's define our target event, which we'll call E. We want to find the probability that both are boys. In our list, there is only one outcome that fits this, BB, so event E is just BB. Fourth, we must find the intersection of E and F. Written as E intersection F, we are looking for outcomes that are in both our target event and our condition. Looking at our sets, the only outcome present in both is BB. Therefore, the number of outcomes in the intersection, or N of E intersection F, is 1. Finally, we calculate the conditional probability. Using the formula for equally likely outcomes that we introduced earlier, we take the number of outcomes in the intersection and divide it by the number of outcomes in our new reduced sample space. That is, P of E given F equals N of E intersection F, divided by N of F. This gives us 1 divided by 3. So, the probability is 1/3. Notice how the condition, at least one is a boy, changed our denominator from 4 down to 3. We will see this same logic applied to playing cards and dice in the next few slides. Card draws and student demographics. Now that we have seen how to handle abstract probabilities and family compositions, let's move on to slide 4, where we look at more practical scenarios, like card draws and student demographics. These types of problems are very common in exams and usually involve looking at a specific subset of a larger group. Let's look at this specific example involving a standard deck of 52 cards. The problem asks, if we draw a card and we already know for a fact that the card is red, what is the probability that this card is a heart? To solve this, we will follow a step-by-step approach, just like we did in the previous examples. First, we need to identify our condition, which we will call event F. The condition given to us is that the card is red. Now, we know that in a standard deck of 52 cards, there are 26 red cards, consisting of both hearts and diamonds. So, the number of outcomes in event F, written as N of F, equals 26. This is our new reduced sample space. Second, we identify our target event, which we will call event E. Our goal is to find the probability that the card is a heart. In a standard deck, there are exactly 13 hearts. Third, we must find the intersection of these two events, which is written as E intersection F. This represents the outcomes that satisfy both conditions. The card must be red, and it must be a heart. Since every single heart in the deck is already a red card, the intersection is simply the set of all 13 hearts. Therefore, N of E intersection F equals 13. Finally, we calculate the conditional probability. We use the formula for equally likely outcomes, which is the probability of E given F, written as P of E given F. This is equal to N of E intersection F divided by N of E divided by N of F. When we plug in our numbers, we get 13 divided by 26, which simplifies beautifully to 1/2, or 0.5. So, once we know the card is red, the chance of it being a heart is exactly 50%. This concept of narrowing down our focus is exactly what we will apply next when we look at more complex experiments involving dice. Dice experiments. Now, let's move on to slide 5, where we will look at dice experiments. As we have seen in our previous examples with family composition and card draws, the key to conditional probability is seeing how a specific condition restricts our possibilities. Dice problems are absolutely excellent for visualizing this concept because you can clearly see how a condition shrinks the total number of possible outcomes. Let's work through a concrete example together. Suppose we toss 2 fair dice. We are given a specific condition. The sum of the numbers appearing on the 2 dice is 8. Our goal is to find the probability that one of the dice shows a 5. To solve this, we will follow a step-by-step approach, just like we did in the previous slides. Step 1, we need to define our given event, which we will call event f. This is our condition. Since we know the sum must be 8, we shouldn't look at all 36 possible outcomes of 2 dice. Instead, we only list the pairs where the numbers add up to 8. These pairs are 2 and 6, 3 and 5, 4 and 4, 5 and 3, and 6 and 2. If we count these up, we see that the number of outcomes in event f, denoted as n of f, is equal to 5. This is our new, reduced sample space. Step 2, next, we define our target event, which we will call event E in this case. Event E is the event where at least one of the dice shows a 5. Step 3, now we must find the intersection of these two events, which is E intersection f. This means we look only at our reduced sample space, the list of pairs that sum to 8, and pick out only those that contain a 5. Looking at our list, we see the pairs 3 and 5 and 5 and 3. So the intersection contains just these two outcomes, meaning the number of outcomes in E intersection f, or n of E intersection f, is 2. Finally, step 4, we calculate the conditional probability. Using the formula for equally likely outcomes that we established on our first slide, we take the number of favorable outcomes in our intersection and divide it by the number of outcomes in our reduced sample space. That is, the probability of E given f equals n of E intersection f, divided by n of f. This gives us 2 divided by 5, which simplifies to 0.4. As we move to our final slides, keep this process in mind. Always identify your new, restricted universe before you start counting your successes. Key takeaways. All right, we have worked through several different types of problems now, from basic probability values to more complex scenarios like dice rolls and card draws. As we wrap up this lesson, let's consolidate everything we've learned into 3 key takeaways. First, I want you to focus on the concept of the reduced sample space. This is the heart of conditional probability. Throughout our examples, whether we were looking at family compositions or sums of dice, you notice that the moment we are given a condition, the original sample space is no longer our focus. The given event, which we call event f, effectively becomes our new, smaller sample space. Everything outside of event f is now irrelevant to our calculation. Second, let's talk about how to choose your formula. You need to look at the information provided in the problem. If the problem gives you specific probabilities, you should use the formula where the probability of E intersection f is divided by the probability of f. However, if you are working with a set of outcomes that are all equally likely, like counting the number of hearts in a deck or the number of ways to roll an 8, you should use the counting method. In this case, the number of outcomes in E intersection f is divided by the number of outcomes in f. Finally, always remember that the intersection is key. When you are looking for your numerator, do not just look for the target event, E. You must specifically identify the outcomes that satisfy both the condition and your target event. It is the overlap, the intersection, that matters. Now, before you finish your practice, let's take a moment to look at some common pitfalls to avoid, so you don't lose marks on these tricky details. Common mistakes. First, be very careful not to confuse the probability of a given B with the probability of B given A when you see that vertical bar. Remember that the event following it is your condition. It is the information you already possess. In other words, the probability of a given B is not the same as the probability of B given A. Always identify which event is the given information before you start your calculation. Second, a very frequent error is continuing to use the original sample space, which we call S, when we move from the basic probabilities we saw in slide 2 to the more specific scenarios like the dice or card examples we just covered. The original sample space is no longer relevant. You must not divide by the total number of outcomes in S. Instead, you must divide by the number of outcomes in your new, reduced sample space, which we call F. Once a condition is introduced, your world shrinks to only include the outcomes that satisfy that condition. Finally, do not overlook the intersection. It is tempting to simply count the number of outcomes in your target event. However, as we practiced with the family composition and the dice problems, you cannot just use the number of outcomes in E, you must specifically look for the intersection of E and F. This means you must only count the favorable outcomes that also satisfy the given condition. Always ask yourself, does this outcome satisfy both my target goal and the condition I was given? Now, as we wrap up this lesson, I want to pause and discuss some common pitfalls. Even if you understand the logic of reduced sample spaces, it is very easy to make a few specific errors in your calculations. Let's look at these 3 common mistakes so you can avoid them in your exams. If you can keep these 3 points in mind, you will have a much stronger grasp of applying conditional probability to equally likely outcomes.